This is a lesson on dielectrics and capacitors and electrostatics. I wanted to cover properties of dielectrics, sort of the big ideas and concepts of dielectrics. Dielectric is an insulating material. Notice that it's insulating. There are no free charges or very few free charges in that material, and that it's placed between the plates of a capacitor. And what I'm going to note here, I didn't draw it out here, but if I have a capacitor here, when we put the material in here, it will not touch the plates of that capacitor. There will still be some air, something that the charges cannot flow freely from the insulator to the plates, some separation that the charges stay within that dielectric. So what we know is that if there is charges on one side and the other of this capacitor, that dielectric, whatever that insulating material is, will become polarized in the electric field between the capacitor plates. What this does, the effect overall, is to increase the capacity of the capacitor to hold charge by a factor of the dielectric constant. So in a previous lesson, we had just worried about if there was nothing in there. If there's just air or a vacuum, you can see that the value is 1. Air is very, 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 very small as well. Remember, air is a very good insulator, so it has a small dielectric constant. We can see with other materials here, they have various, this is alphabetical order, they have various dielectric constants. And whatever this value is, you just put it in here, and it's a multiplier for that capacitor. You can see all of them are greater than 1, so the capacitance will always increase. You're increasing the capacitor's ability to hold charge. That's what a dielectric does. It decreases the density of the electric field by a factor of the dielectric constant. And I'm going to show you how this works on the next slide. And also, because the capacitance is increasing, it would increase its capacity to hold charge, but if no more charge is available to collect on those plates, the potential difference between the plates changes. So if Q stays constant, if this stays a constant value, if I increase the capacitance, then the voltage between those two plates changes. So you can see how the dielectric in there is going to play with the important quantities that come out of a capacitor. Let's look at the effect of a dielectric on the electric field. In this situation here, right here, notice that I don't have anything in between. I have the original capacitance, C0. There's no kappa in here. Kappa is 1. Kappa equals 1 in this situation. And we have some sort of original electric field from one charge to the other. Okay, so that all of that is true. When I put the dielectric in here, I made a note up here. We're going to have a new capacitance, and it is kappa times the old capacitance, right? There's the same area and the same distance between the plates. All we did was multiply by this kappa factor. So we have a kappa, an increased capacitance. So what happens in here, when we put, you may remember, when we put an insulator in an electric field, it becomes polarized itself. You can see that here. If I just put this substance between these capacitor plates, you can see that the negative signs are going to be attracted to the positive. The positive is going to be attracted to the negative. They're going to polarize in there. This is an insulating material, so the molecules will reorient. There are no free charge carriers in here, so there won't be a polarization in that way. They will stay in spot and just reorient their polarization in that direction. Well, within that substance, and let me get maybe a bigger vector here. Within that substance, I will have the positive signs here and the negative signs here, and there will be a back electric field due to the dielectric in the other direction. And you can see what that causes is a new electric field value. There is a new electric field in here. I haven't changed number of charges on the each side, but because of this extra charge in the middle, it changes the electric field. So the OpenStax text has a picture of this as well. There's the reference there, College Physics by OpenStax. And you can see that there's the original electric field outside here due to Q on the two parallel plates. But inside, there's the polarized molecules. Their electric field will flow in the other direction. And so you get this flow in the other direction, and it reduces. So when I look at the effect of the dielectric on the electric field, E nu will be less than E of the original situation. And we also know that's consistent with what we expect. It will decrease the electric field, and that means it decreases the voltage, right? V equals ED. The distance doesn't change. If the electric field decreases, then the voltage must also decrease as well. So that's the effect of the dielectric on the electric field and voltage in the capacitor. I picked out a really simple application, a really cool application, I think, of a capacitor is a cell membrane. And I had talked about a cell membrane in a previous lesson. There's an electric field in the cell membrane, and there's positive charges on the outside of the cell and negative charges on the inside of the cell. The membrane that surrounds certain type of living cell has a surface area of 5 times 10 to the negative 9th meters squared. So I'm going to note that's the area that goes into the capacitor equation. That's the area, 5 times 10 to the negative 9th meters squared. Okay, and I know that there's a distance between the outer and inner surfaces of that membrane, but what we're going to assume is that the distance between those two surfaces is much, much smaller than the radius of that cell. Okay, so the radius of that cell is really big, so the distance, it matters for the capacitance. But for the area of the inside surface is going to be approximately same as the area of the outside surface. It tells me the thickness as well. The D is 10 nanometers, so that's 10 times 10 to the negative 9th meters. Okay, so assume the membrane behaves like a parallel plate capacitor and has a dielectric constant of 5.1. So there's the kappa 5.1. And we have all these things. You could possibly calculate the capacitance here, kappa epsilon naught A over D, and plug all those values in. When you calculate this, though, you get 2.258 times 10 to the negative 11th farads. Or you could call that 22.58 picofarads, 10 to the negative 12th. Okay. So we know that about the capacitor. Let's read on. It says the potential on the outer surface of the membrane is plus 60 millivolts greater than that on the inside of the surface. So let's draw this surface here. I'm going to draw it like this. I know this would be plus 60 millivolts, and I'm going to put this at 0 millivolts. So the electric field goes from outside the cell to inside the cell. So this is out, and this is in, and this is the electric field. So they say this is a parallel plate capacitor. How much charge resides on the outer surface? That's what we're looking for. So we're looking for Q. That has to equal C times V. Okay, well, the C value I can find, kappa epsilon naught A over D. Those are all quantities that I know. And then the voltage they give me is the 60 millivolts. So I can write all that stuff out and put it in my calculator. So the kappa is 5.1. Epsilon naught 8.854 times 10 to the negative 12th. The area is 5 times 10 to the negative 9th, and the voltage is 60 times 10 to the negative 3rd. I just multiplied all the way across there, and then when I multiply that and then divide by the distance between the outer and inner membranes of the cell is 10 times 10 to the negative 9th. And when you run that through your calculator, you get a net charge of 1.354662 times 10 to the negative 12th coulombs. So that's a picocoulomb. You can just leave it like that. That would be a fine answer there. Or you could write it as 1.35 picocoulombs. So that is the charge. Let's look at B. B asks, if the charge in part A is due to positive ions, how many ions are present on the outer surface? So a positive ion, we're going to assume, is just a charge of +1. You don't see that in there. So a charge of +1. So how many +1 ions are on the outside? So the number of them, I will take the total charge and divide by the elementary charge. Each singly charged ion has the elementary charge on it. So I'll take 1.355 times 10 to the negative 12th and divide by the elementary charge 1.6 times 10 to the negative 19th. And you can see we're going to get a lot of ions on here. You get 8, 4, 6, 6, 6, 3, 7.5 ions. So that's about 8.5 million ions. That's not the total number of ions, obviously, but that's the number of ions that has accumulated to have a net charge on the outside of the cell and on the inside of the cell.